I work in a field called algebraic geometry. You see, in mathematics, there are certain basic things we start with. We know about numbers, we know about shapes, and then a little beyond that, we try to put those things together to do little more advanced processes which are involve infinite or continuous things. These are sort of basic things, but then there are other structures in mathematics which take these and go to a higher level things, combining several of the fundamental things. Algebraic geometry is that kind of field. It combines number theory, geometry, algebra, calculations, all of those together to try and study certain problems. One definition is that these are spaces which are solutions of certain types of systems of equations. And what is special are the types of equations. These are what are called polynomial equations. Things like x squared plus y squared plus z squared equals 17. Something like that. That involves certain things. It's different from sin x plus cos y plus something with trigonometric functions. No, they are more complicated, different types of functions. Algebraic geometry involves polynomials, which are the simplest functions beyond the linear functions. I myself am interested in some aspects of algebraic geometry which are related a little bit to number theory. So algebraic geometry is a thing where on the one hand you can use geometric intuition of the kind which we have from space and so on, from our world around us, but at the same time you can transpose that intuition to questions coming from number theory. So you have things like finite fields and modular arithmetic. Related to that, there are certain structures which are like structures in geometry. So I'm trying to study some of those things. Covering spaces, they call them. For the last several years, I've been studying things related to that in the context of number theory. Because it's a sort of higher level subject, it is actually behind many types of calculations which you can do in different fields. Though, if I can put it like this, more abstract subjects take time to percolate into other parts of mathematics. So in that sense, algebraic geometry is one of those things which it is more and more penetrating into different parts of mathematics, but there is still scope for that to happen. At the level of pure mathematics, it is a fundamental discipline. It is there throughout a lot of pure mathematics. It influences it. Oh, there are aspects of algebraic geometry connected to physics also, or at least which those parts of the subject sort of talk to each other, so to speak. That's one aspect of algebraic geometry. There's another aspect which is related to number theory. There's a third aspect related to differential geometry and those kinds of things, you know. Being something like, it is related to basically pure mathematics, so direct connections with the daily life are not so easy to find right away. But there are hidden applications, things to do with coding, for example, error correcting code. There is some algebraic geometry which goes into designing those things. So that's an aspect of things. But I'm not the most expert person on that side of the subject, but and I do know people in who have come from other kinds of mathematics, related even to, which were motivated by questions from things like business, to do with manipulations of large data sets of numbers. Somehow algebraic geometry helps those people to do the calculation. I can't say I personally understand how it works, but I know there are people who do that. I initially actually was interested in number theory as a student, and then I decided somehow in order to properly understand number theory, I have to first learn algebraic geometry, and somehow I ended up being diverted towards that subject instead. I do have some interest in number theory still, but I'm not a specialist in that field. I'm more of a specialist in algebraic geometry. The nice thing I like about algebraic geometry, maybe I should say this in this sort of a setup, it brings together different parts of pure mathematics and the connections between them. That's one of the nice things about the subject. You can use things from one part of mathematics to study a problem which seems to be coming from another part. It's not obvious right away that they're connected, and that is the fun, to try to find those connections. It's hard to say that a particular one is more difficult or less difficult. It seems difficult when you do it. Then 20 years later you think, well, maybe I should have been smart and figured it out more quickly. But one question where I was happy with the solution, it was exactly like I was trying to explain earlier, that it made an unexpected connection. I was trying to find the dimensions of certain spaces which formed a sequence of spaces, and I want to know how the dimension changed. These spaces are spaces over the complex numbers, usual vector spaces. But in order to solve the problem, I had to see a connection with something called p-adic numbers, which is something from number theory. It's not obvious right away that it has anything to do with the problem, but that turned out to be the real insight. It was not obvious. I was very pleased that I managed to see this connection. That was all. Artificial intelligence does already seem to be impacting some specific areas in mathematical research. There are very nice articles. There are articles in the Quanta magazine explaining how there are examples people have used AI to do pure math research. One thing, a mathematician called Jordi Williamson, he and his collaborators have managed to take large data sets which came from the theory of knots. Knots are certain structures, and like you tie a knot, there's a mathematics of these things, and knot theory is an active area of research. There's lots of data about knots, and artificial intelligence was used to make predictions that certain knot invariants might be related to certain other invariants. It's not obvious that, mathematicians didn't expect a relation, but the AI found the relations. AI suggested that this invariant must be related to that one. Once the AI suggested the connections, then they did experiments. Remove little bit of the data, how does the conclusion change? So which parts of the data are important? AI again was able to help them with that. Then they could come up with a mathematical program, and then they implemented the program. So this is something where AI was like a partner in the research. So there are examples, a few. Anything involving lots of data where you want to make sense. Is there a pattern which I can't see? It's too big, there's too much data. The computer might be able to see patterns which are hard to see directly as a human. When I do research, sometimes I have to do a calculation in a problem to develop my intuition. The AI and those things can do other kinds of calculations which are not easy for us to do as humans. So that way it can help.